Alright, let's talk about the history of the atom, or what's commonly known as atomic theory. So, yeah, theory. Atoms, we've never really seen them. We don't really know what they look like or what they're composed of. However, we have made several observations, inferences, ran tests, built models, and as a result, we've developed a theory of what we think the atom looks like. It's a very well-founded theory because of all the different things we observed and all the different things we've tested, but we've never seen an atom before. So as far as its structure goes, we will never know for sure if what we're guessing is true, but we're pretty certain, 99% certain, based upon the evidence we've gathered. So let's just start by talking about what we may or may not know about the general structure of an atom. So this is all stuff from, freshman chemistry. So atoms have that densely packed region in the center, and that's called the nucleus, and that's where the protons and neutrons are. So it's that densely packed region, protons and neutrons, and remember, protons are positive, and neutrons are neutral, so we symbolize those with just a dot. Since neutrons are neutral and protons are positive, that means in general the nucleus has a positive charge. So it's a densely packed positive region in the center. It's called the nucleus. And then surrounding that nucleus is what we generally call the electron cloud. And so it's just a region where the electrons are found. And electrons are negative, and so typically I symbolize them with an E negative. That just means electron. So we've got protons and neutrons that are found in the nucleus, and then surrounding them is the electron cloud. We'll go more into depth about what this cloud looks like. It's not a nice little egg shape like this. Instead, there's certain regions and shapes that the electrons follow as a pattern. But this is the general structure. We have a densely packed region in the middle surrounded by a negatively charged area, and that's the atom. That's what we currently accept as the model for the atom, this basic layout. Now there's things smaller than this, quarks and neutrinos and all of that kind of stuff, but we're not going to concern ourselves with that. We're just going to focus on just the atomic theory of what we're seeing right now. So let's kick it off old school style with Democritus in 400 BC. He was a Greek philosopher, so he wasn't really a scientist or even a chemist. Instead, he was a guy who would sit around and talk about things, so philosophers wonder stuff like, do dogs think, or why are we here, stuff like that. So one of the questions that they sat around their little powwow circles and talked about was, what is everything made of? So what they started saying was, okay, if we were to take a rock and we were to cut it in half, we would still have a rock. And if we cut that half in half again, we would have half of that half, and we could keep doing that on and on and on. So what philosophers accepted at this point was that you could do that forever. So that you could always, if you had a knife small enough and a microscope that could see powerful enough, you could always, in theory, cut something smaller and smaller and smaller and smaller. It would never get small enough to where you couldn't cut it. Democritus said, no, I think you're eventually going to hit a point where you'd reach an uncuttable piece. So a basic fundamental building block that could not be cut any smaller. So if you were to take something like a sugar grain, and you were to cut it in half, you could keep doing that, but eventually you would hit a single piece that could not be cut any smaller. The word that he used to describe them was atomos, which means uncuttable. Now, unfortunately, his successor, who learned at his very knee, didn't believe in atoms, so he believed that you could cut things smaller and smaller onto infinity. So, unfortunately for scientific progress, the idea of an atom died here. And then for hundreds, nay, thousands of years, almost 2,000 years, the idea of the atom was flushed to the side, and we never thought about it. In fact, it was Einstein who essentially proved that atoms exist. Up until Albert Einstein, society thought there was no such thing as an atom. We had no idea. Think about this, you guys. We've grown up knowing about atoms and hearing about them and just kind of taking it for granted. 100 years ago, they didn't think atoms existed. So what's changed between now and 100 years ago that led us to believe that, yeah, there is things called atoms? So we'll start our modern trip, or more modern, in 1743 with Antoine Lavoisier. So he was a French nobleman and also referred to as the father of modern chemistry. So what he brought us was the law of conservation of mass. And the law of conservation of mass says that matter can't be created or destroyed. So if you were to react two things together, your products are going to weigh exactly what your reactants weighed. You're not going to wind up with extra mass or less mass. And this was a puzzling idea because, like combustion, if you burn something, you wind up with less than what you started with, right? So Lavoisier built a machine, looks something like this, and what he was able to do then is when he burned things, he was able to collect them and then get their mass before and after. And he found out that no, nothing's really being destroyed. We wind up with the same mass afterwards as what we started with to begin with. Along the way, he also discovered several elements, so basic building blocks. He discovered and named oxygen, hydrogen. He proposed that sulfur was an element. He even thought about silicon before it had ever really been discovered. He did a lot of research into combustion, found out about oxygen and the role it plays in burning, but really the big thing that he brought to the world of chemistry was this law of conservation of mass. Matter cannot be created or destroyed. Okay, now John Dalton. John Dalton was in 1808, and he was an English school teacher. He didn't teach English, he was from England, and he taught school, like all the subjects. So what he did was he proposed the atomic theory. So he did a little bit of research, but a lot of his stuff was just looking at what other researchers were doing. So he looked at what Lavoisier did, he looked at even what Democritus said, and he kind of put it all together into the atomic theory. So he proposed this idea that all matter is composed of extremely small particles called atoms. Now, keep in mind, he was just proposing this idea of atoms. He had no proof that they existed. That was Einstein in the 1900s who proved their existence. But he said, and he got the word from Democritus, that all matter is composed of these small, uncuttable particles called atoms. And he said that atoms of a given element are identical in size, mass, and other properties. So if you have a carbon atom here in Dallas, Oregon, and a carbon atom in Australia, both of them would be exactly identical. Okay, they have the same properties, therefore the atoms look exactly the same. He also said atoms cannot be subdivided, created, or destroyed, so there's nothing smaller than an atom. Once you hit the atom, bam, that's it, end of the road. And then the last one, atoms of different elements combine in simple whole number ratios. Now, for the most part, this still holds true. We still follow the atomic theory, and we still learn it in chemistry because it's, for the most part, true facts. So, a couple things that are wrong here, though. With part number 2, it says that atoms of a given element are identical in size, mass, and other properties. We now know that's not true. Okay, they can change in both size and mass. Their properties are still pretty much the same, but isotopes, which have different weights because of different numbers of neutrons, still have the same property, so they're still identical, but their mass and generally their size are going to be slightly different. But for the most part, a carbon atom here in Dallas, Oregon, and one in Australia are going to be the same. Atoms cannot be subdivided, created, or destroyed. So we know a couple different things about that now. They can be subdivided, so there is things that are smaller than the atom. Those are protons, neutrons, electrons, and now quarks and Higgs bosons, and all of those. Created and destroyed, well, you can't really destroy an atom, but you can convert it to other things. We know from the atomic bomb and nuclear power that you can take the mass of an atom and convert it into energy. So while atoms can't be created or destroyed, they can be converted into other things. And then the last postulate, the fourth one there, still correct, but we'll talk a little bit about what that means. So atoms of different elements combine in simple whole number ratios. So they had known already that water was composed of hydrogen and oxygen. And they knew that the ratio of the masses was the same, but they thought it was just kind of like a hydrogen-oxygen thing kind of lumped together. So if hydrogen and oxygen were touching, therefore it would make water. What he proposed, though, is that it had simple whole number ratios. And so water wasn't just hydrogen and oxygen pushed together. Instead, it was 2 parts hydrogen, 1 part oxygen. And this was found through various experiments. And then from that, we could also see things like H2O2, which also has hydrogen and oxygen, but it has a different ratio. So in water, it's a 2-to-1 ratio. In hydrogen peroxide, it's a 1-to-1 ratio, or 2-to-2. So this then explained how you could get different compounds from the same elements. Hydrogen, or water, and hydrogen peroxide behave extremely differently. Even though they're made of the same building blocks, they have different whole number ratios. And it's always whole numbers, so you would never have something like H 1.3, O 2.7. Okay, it's always whole numbers. So 2, 1, 3, 4, 5, etc., etc., etc. So in the late 1800s, early 1900s, there was a huge boom in scientific research due to the discovery of, or the harnessing of electricity and nuclear power, radiation, I should say. And so one of those things was J.J. Thompson. So I've told you before, science is nothing but nerds with toys. And so here we have our nerd, the nerd being J.J. Thompson, and here we have his toy. Okay, so J.J. Thompson, he got this toy, this cathode ray tube, which is a really cool device that when you hooked it up to electricity, so a cathode and anode, it would produce this beam that went across it. Now, from other experiments with paddle wheels, they knew that this beam wasn't just light, it was composed of matter. There was particles in it, so it was like little chunks being thrown from one side to the other. What he did then, and so you can see him up here with his cathode ray, is he took a magnetic field, and he found that if he put a positive charge and a negative charge next to the cathode ray tube, he could actually make that beam deflect. And so this beam, rather than just traveling straight through, would actually deflect away from the negative and towards the positive. So it was being repelled by negative and attracted to positive. All right, so he put some pieces together here then. He said, all right, we've got a beam that's composed of particles, so it has substance to it, and it's deflecting away from a negative and towards a positive. Therefore, this beam, it's not just light. It has to be something with mass, and it has to be something negative since it's repelling from negative and going towards positive. And so he proposed then that there must be something that he called the electron. J.J. Thompson, this nerd with his toy, made the first discovery about subatomic particles. So things that were smaller than the atom. What makes up the atom? This electron, a negatively charged particle, opened up the doors to the idea that, okay, atoms are more than just these uncuttable pieces. They're actually made of things themselves. And the cathode ray tube itself went on, they did other discoveries with it and actually found a lot of products, televisions, computer monitors, lithoscopes, all kinds of different things are made from cathode ray tubes. Even plasma TVs use this basic idea right here. Alright, so let's bring ourselves up to date with the atomic theory. So right now we've looked at J.J. Thompson, and what J.J. Thompson found was the electron. And also the basic understanding of the atoms now is that they were neutral. And so if the atom is neutral, that means it has no charge. So J.J. Thompson's discovery of the electron means that there had to be something to cancel out that negative charge. And so then it was proposed then there must be something positive as well that made up the atom. So then they kind of assumed at this point then that atoms were made of electrons and protons. So they had to come up with a model to kind of coincide with that. So what they developed was what's known as the plum pudding model of the atom. Now, plum pudding, we don't really recognize that because we're Americans, and this is the year 2013. But back in Britain in the 1900s, plum pudding was like a dessert. And it's not really pudding so much as what we think about it. This is more like a piece of raisin bread. Raisin bread would be a better analogy for us Americans. So if you imagine raisin bread, it's a piece of bread, and baked into that bread there is raisins. So scattered hither and yon, you have little raisins flecked throughout the bread. Now, this is what they assumed the atom looked like, not like a slice of bread, but instead you had this positively charged mass, and so imagine the bread itself as being just a giant positively charged thing. Okay, so they assumed, like the bread, positively charged, and then flecked throughout the positively charged bread was these electron particles. And so this was then the plum pudding model of the atom. Plum pudding would be it's almost like a bread with plums baked into it. So you can picture the same thing. It's this positively charged mass with electrons put into it. And so then they assumed really that an atom looked like this, just a circle with electrons kind of scattered throughout it. And enough electrons then to neutralize out the overall positive charge of that entire mass. Now, knowing what we know about the atom, this looks ridiculous. It doesn't look like what we picture as an atom, especially that one that we drew at the beginning with the nucleus, the electron cloud. They imagined it all as just one large blob almost. in steps Ernest Rutherford in 1911. So this New Zealander, he was the man in chemistry. What he came up with was brilliant. The experiment that he set up was the absolutely most ridiculous experiment ever. Had no logical reason whatsoever to run this experiment, but the fact that he did brought us to what we know about the atom today. If he wouldn't have done it, and for whatever reason he did it, we would not know what we know today about the atom. So this absolutely ridiculous experiment that we're talking about, what he did was he took what's called alpha particles. So he took a generator that makes alpha particles, and those are symbolized with a little fish. So about this time they were discovering a lot about radiation. Alpha particles is a form of radiation. It's one of the biggest radiation particles. And they knew that if they put it inside of a lead box with a tiny hole drilled in it, they could actually make a gun that fired alpha particles. Pew, 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 pew. And so they would shoot these alpha particles, and they would use that phosphorescent screen. So like what we saw in the cathode ray tube, it's a screen that when hit by particles, it will make a little green glow. So anywhere that those alpha particles would strike that phosphorescent screen, it would glow green. And so you would know then that the alpha particles are hitting, right there because it's making a little green blip. So on the subatomic world, alpha particles are very large. They're about the size of a helium atom, which isn't very big to us, but in the atomic world it's fairly large, and they fly with a pretty good amount of power. And so as far as atoms go, this is large, and these are pretty powerful. It's like shooting a pretty large bullet. So a ridiculous thing number one that Ernest Rutherford did. He told his grad student, so these are his little minions that he had playing with his toys, take that alpha particle generator, take your translucent screen, and put a thin sheet of gold foil in between it. And so they took a thin sheet of gold foil. Imagine like aluminum foil, only much thinner, made out of gold. The cool thing about gold can be stretched so thin that it's only a few atoms thick. And so that's what this was, just a fine, thin piece of gold foil that they shot alpha particles through. And as expected, they could see the alpha particles blipping through to the other side. So the alpha particles went straight through the gold foil. Big whoop. That's what they expected to happen, and that's exactly what happened. Ernest Rutherford, he was a brilliant scientist, and his minions, they looked up to him, and they would do what he said just because they had such respect for this guy. And so when he told them to sit in the dark and watch these blips appear on the screen, they did it, and they did it for days. It did exactly what they expected, and it kept happening. Eventually, Rutherford happened to walk by these guys, and he said, how's your experiment going? They said, oh yeah, it's happening just like we expected it to happen. And he said to them, you know what, take that phosphorescent screen and move it. Instead of just watching on the opposite side of the particle generator, why don't you bring that phosphorescent screen over to the opposite side and see if you see anything? This is one of the most inconsequential yet important suggestions from the entire history of chemistry. He told them to move it so that they were watching instead of right behind the particle generator on the same side as the particle generator. So they took the phosphorescent screen and they moved it over here on the same side as the particle generator. Now, there is absolutely no reason for there to be anything to be seen on this side of the alpha generator. But what they found is that 1 in 8,000 shots that were fired, that's right, 8,000 shots would be fired, and one of them would produce a blip on the same side as the gold foil. Big whoop, they saw the blip on the same side as the gold foil. If you're not impressed by this, think of it this way. Rutherford described it as taking a .50 caliber bullet shell, firing it at a piece of tissue paper, and having it bounce back at your head. Would that surprise you? You bet it would surprise you. This surprised them. The alpha particles were not shooting straight through the gold foil. Most of them were, 7,999 of them were, but 1 out of 8,000 would ricochet off the gold foil and bounce back. In the plum pudding model of the atom, this shouldn't happen because this is a piece of tissue paper to this .50 caliber bullet. If we're firing this at this right here, it should shoot straight through. There is absolutely no reason why anything would come back at their heads. This crazy, off-the-cuff, absolutely no reason suggestion of moving the phosphorescent screen back to the same side led to the discovery of the nucleus inside of the atom. No longer did they think of the atom as a plum pudding. There had to be something more to it. This discovery led Ernest Rutherford to propose an atom that had a nucleus, the nuclear atom. What he said those alpha particles were bouncing off of was a nucleus. So there was something at the center of the atom that was densely packed and positive. That was the nucleus. And then surrounding the nucleus was a large area that housed the electrons, which he called the electron cloud. So instead of that positive occupying the entire atom, it was densely packed into the center. And so when those alpha particles were fired, pew, 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 at the nucleus, the ones that ricocheted were the ones that were hitting that nucleus. The ones that went straight through, so the 7,999, were the ones that were fired through the electron cloud. So two things that Rutherford proposed about the atom from this experiment. One, that there was a nucleus, a densely packed positive region in the center that alpha particles would ricochet off of and bounce back towards their heads. And second, that the most of the volume of the atom is empty space. So this densely packed region, this nucleus, it is not drawn to scale in this picture. If 7,999 of them were going straight through and only one was bouncing back, that means that this densely packed region is tiny with comparison to the rest of the atom. And electrons are also very small, so that means that most of the atom is just empty space. All of this area between the electrons and the nucleus is nothing. There is nothing there. So there is a nucleus in the center, and an atom is mostly empty space. Picture it this way. If this electron cloud was the size of a football field, then the nucleus would be about the size of a marble. Here's another way to picture it. So your body obviously is made of atoms. Most of the atoms in your body are nothing but empty space. If it were possible to remove all of the empty space out of your body, out of the atoms that are in your body, your entire mass would fit into an area smaller than a grain of sand. That means the difference between you and a grain of sand is empty space. Now, here we are looking at this atom with a nucleus and the electron cloud. This is where we stand today. Ernest Rutherford and his minions brought us to this discovery based upon an absolutely ridiculous experiment that had no reason and was miserable for those who were doing it. Here is Rutherford's two minions that did this experiment, Hans Geiger and Ernest Marsden, both of them who went on to be great scientists themselves. To kind of give you a picture of what's going on here, so it's not like they could sit back and drink a Dr. Pepper and watch these blips happen. They had to stare through a tiny little microscope to watch the blips. And so these guys would stand in absolute dark with a machine that looked something like this, staring through a microscope at a phosphorescent screen for days counting blips. 1 in 8,000, that means they were counting at least 8,000 blips for every one. And obviously they saw plenty of them that ricocheting back. And you couldn't just sit back and watch all of the blips happening at once. They had to move this microscope around and watch in all of the different areas. So if they were sitting here watching that, they wouldn't see those blips right there. This would be tough. But yet they did it because they respected Rutherford and they knew it was for the betterment of science, and it was. So you can thank those three characters for leading us to what we know about the atom today.